One image closed the last video. Three separate timelines, an algorithm, a dataset, a piece of borrowed hardware, arriving in the same room in the same year. That convergence has a name you've probably heard before but never had explained: deep learning. Not a new algorithm, not a new dataset. Somehow, the same three ingredients that produced one extraordinary result in 2012 didn't stop there. They started something that hasn't slowed down since. A trend, not a single good year. So what does deep actually mean? And why did this particular convergence keep compounding instead of being one great result that eventually plateaued? That's what closes Act 3.
Plain machine, AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue.
Start with the word itself. Deep doesn't refer to how smart a network is or how complicated its math is. It refers to something much more literal: how many layers of neurons sit between the input and the output. A shallow network, the kind Video 9 and Video 10 described in principle, might have one hidden layer. A deep network might have a dozen or 100. That number is the entire definition. Everything else follows from it. Here's why that number matters so much. Each layer in a network doesn't just repeat what the layer before it did. It transforms it into something more abstract. Feed a network a photograph, and the first layer might learn to notice simple things: edges, patches of contrast, the border between light and dark. The next layer doesn't see the photograph at all. It only sees what the first layer found, and it learns to combine those edges into something slightly more complex: a curve, a corner, a texture. The layer after that combines those into something more complex still, a shape that might be an eye, or a wheel, or a leaf. By the final layers, the network isn't looking at pixels anymore. It's working with something closer to concepts. Nobody wrote any of that. No engineer sat down and coded, "This is what an edge looks like," or "This is how eyes combine into faces." Every one of those layers learned its own features directly from data, the same way Video 10's mechanism always worked: backpropagation, adjusting weights, layer by layer, based on what reduced error. The only thing that changed in 2012 was that there was finally enough depth, enough data, and enough hardware for that hierarchy to actually form. Compare that to the traditional approach computer vision used before 2012, the one Video 11's competition results were measured against. Traditional systems relied on hand-engineered features, a researcher deciding in advance what mattered and building the system around those choices. It worked up to a point because human intuition about what matters in an image is genuinely useful. But it also meant the system could never learn anything the researcher hadn't already thought to look for. A deep network has no such ceiling. Its features aren't chosen, they're discovered. Take one concrete case. Feed a deep network a photograph of a cat, one it's never seen, after training on millions of labeled images. The first hidden layer doesn't know what a cat is. It only knows to react to edges and contrast, the boundary between fur and background, the outline of an ear. The second layer takes those edge reactions and starts combining them. A curved edge plus a pointed edge, repeated in a certain pattern, starts to look like a triangular ear shape or a whisker. By the fourth or fifth layer, combinations of shapes start to resemble parts, not just patterns: an eye, a nose, a paw. By the final layer, the network isn't reasoning about pixels, edges, or even parts anymore. It's asking one question. Given everything this stack of layers has found, how closely does this match the pattern that got labeled cat during training thousands of times over? That's the entire operation, top to bottom. No step in that chain was designed. Every one of them was learned. Here's the part that turned one result into a trend. The same depth principle, stack enough layers, let them learn their own features, doesn't care what kind of data it's given. Within 2 years of 2012, speech recognition systems that had relied on decades of hand-engineered acoustic modeling started being replaced by deep networks that learned sound patterns directly from audio waveforms, the same way the vision networks had learned from pixels. Machine translation followed a similar path not long after. Every one of these fields had spent years building hand-engineered systems, tuned by specialists who understood that specific domain deeply. And in each case, a deep network, using the same core idea proven in 2012, adapted to a different kind of input, matched or beat those hand-tuned systems within a few years. That's not a coincidence repeating itself. That's evidence that the underlying idea was never actually about images. It was about learning hierarchical structure from raw data, whatever that data happened to be. Vision was just the first room the idea walked into. So why didn't this plateau the way earlier AI breakthroughs so often had? Because proof changes incentives. A result this visible, a 10-point collapse in error rate, reproduced and then beaten in other domains, pulled funding, researchers, and infrastructure investment toward deep networks at a pace nothing in Act 2 ever saw. More funding meant bigger data sets got built. More researchers meant faster architectural improvements. Better infrastructure meant training runs that would have taken a month in 2012 took a day by 2015. Each improvement made the next result easier to produce, which pulled in more investment, which made the next result after that easier still. Nothing about the algorithm changed to cause this. What changed was that for the first time in the field's history, success fed directly back into the conditions that produced more success. That loop, not any single paper, is what "why now" actually means. So, what does this actually change about how you evaluate an AI system marketed as using deep learning? 2 scenarios worth working through. Scenario 1. A vendor tells you their product uses deep learning, as though that phrase alone certifies quality. It doesn't. Deep learning describes an architecture, depth, and the ability to learn its own features, not a guarantee of performance on your specific problem. The right question isn't whether depth is involved, it's what data that depth learned from, and whether that data resembles the situation you're actually going to use it in. A deep network trained on one distribution of examples can be extremely confident and extremely wrong the moment it meets a distribution it never saw during training, because whatever features it learned were learned from that training data specifically, not from the world in general. Scenario 2. A team tells you their deep model can't explain why it made a particular decision. This isn't evasion, it's a direct structural consequence of everything in this video. A hand-engineered system could point to the rule that fired. A deep network's reasoning is spread across potentially millions of learned weights, arranged across dozens of layers, none of which were designed to be individually readable by a human. That trade-off, self-taught features in exchange for reduced interpretability, isn't a bug engineers overlooked. It's the same trade every deep system makes, and it's worth asking about directly whenever the stakes of a wrong or unexplainable decision are high. Depth bought capability. It didn't buy transparency for free. Trace the whole arc one final time. 1958, the perceptron. 1969, Minsky and Papert prove a real narrow ceiling, and the field mistakes it for a verdict on the entire idea. 1986, Rumelhart, Hinton, and Williams proved the ceiling was local, not fundamental. 2009, a dataset finally exists large enough to test what depth could actually do. 2006, in a completely unrelated industry, hardware built to do millions of things at once. 2012, all three converge, and a 10-point collapse in one competition becomes the first data point in a 5-year expansion across nearly every field that touches raw data. Here's the tweetable version. Deep learning isn't a new algorithm, it's the old algorithm. Backpropagation from 1986, run deep enough to learn its own features, edges, then shapes, then objects, with no human writing any of those rules by hand. That's not why it worked once in 2012. That's why it hasn't stopped. Act 3 is complete. The architecture that refused to die in 1986 didn't just survive, it became the default. 3 ingredients built one convergence. One convergence, given enough depth, taught itself to see, to hear, and eventually to read. That last part is where this series goes next. Every deep network in this video learned by finding structure in something concrete, pixels, sound waves, physical signals. Words aren't like that. There's no edge to detect in the letter C. So Act 4 opens with the question depth alone can't answer. If a network needs raw structure to learn from, what does that structure even look like for language? That's Video 14, Word to Vec and Embeddings. The moment words became something a network could finally learn from. Subscribe if you want the full arc. Each video in this series builds on the last. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.